Hello, we're going to look at the Intelligent Gain Block from Enoki Wave. Active antennas offer many advantages for high frequency and millimeter wave applications. They are able to point and steer a highly directional beam in space to overcome challenges of free space path loss and to maintain a robust signal link to moving objects or changing channel conditions. They are comprised of a row or an array of discrete radiating elements, and by controlling the amplitude and phase of how signals at each of the discrete elements are summed together, the beam can be steered or scanned in space. This technique for controlling the signal phase at each antenna element also results in the antenna sometimes being referred to as a phased array antenna. The ability to change the direction of the beam electronically removes the need for any mechanical scanning requirements, resulting in a smaller and low-profile antenna. The beams can also be steered extremely quickly and also shaped to change the antenna performance. Active antennas have already been used for many years in applications like radar or secure communications. Traditional manufacturing, though, has been using modular components which have resulted in a bulky or large form factor, complex and expensive assembly techniques, and excessive weight and power dissipation. Breakthroughs in semiconductor processing and the high-volume, high-precision assembly techniques pioneered by the likes of commercial and consumer handset industries now means that the same techniques can be applied to active antenna designs and manufacturing, enabling an entire new set of new applications and markets where they can be used. Some of these markets include the traditional application areas like radar, imaging, and satellite communications. They can also add additional flexibility and improved performance to other application areas like satellites on the move, where the increased weight and drag effects of mechanical antennas on aircraft aerodynamics can be replaced by low-profile electronically scanned antennas. And they enable brand new markets like millimeter wave communications for cellular and mobile users, where being able to steer a highly directive beam is critical to establishing and maintaining a communications link. All this is made possible by the high integration capabilities of advanced silicon semiconductor engineering. Whereas in the past it was almost impossible to integrate all of the required electronics to steer an electronic beam behind the physically small area or aperture of the active antenna, the high integration available in modern-day silicon processes means that all of the required electronics can be placed close to the antenna as possible. This means that a low-profile planar antenna can be manufactured using standard surface mount assembly techniques, and it also results in the most energy-efficient solution for the link. This is important for reducing the size, weight, and power required to install an active antenna, and also reduces the energy required to power the antenna, an important consideration when energy efficiency demands are increasing with green technologies. The Enoki Wave AWMF 141 and 143 are two examples of highly integrated silicon solutions that can be used to enable a number of different active antenna application solutions. They cover the Ku band between 10.5 to 16 GHz or the lower Ka band frequency of 26 to 30 GHz. They are fully bidirectional intelligent gain blocks that can be used in either a transmit or receive path to provide variable levels of gain control with either high linearity or low noise performance. They also include 6 bits of amplitude and phase control for vector modulation or calibration control with fully independent gain and phase control in each path. They're easily controlled with a standard SPI digital interface. In addition, their extremely small form factor means they can be placed almost anywhere within the assembly. The Enoki Wave AWMF 116 and 117 are very similar in their architecture and flexibility, but they also integrate a diversity switch at the antenna port that enables an additional degree of flexibility, allowing 2 operating modes to be supported by a single gain block. Otherwise, the form factor and control interface are exactly the same, meaning a high degree of flexibility again can be easily integrated and controlled almost anywhere within the transmit and receive chains. Let's look at a couple of examples of how and where the Intelligent Gain Block can be used to enable different active antenna architectures. The component is small enough that it can be mounted directly behind every radiating element in an array, allowing for full flexibility in 2-dimensional beam forming and beam steering. This can be used for all silicon array applications for telecommunications or radar sensing functions. Enoki Wave patented technology means that antenna calibration is not required. Alternatively, the single channel transmit receive block can also be used to enable the traditional column-fed array architecture when integrated with an external front end, typically a PA, LNA, or a transmit-receive switch module. Enoki Wave makes it easier for you to evaluate all of our active antenna ICs with a fully integrated developer kit that includes an IC already mounted on a connectorized evaluation board, a support test kit including all of the evaluation cables and interface circuitry that you'll need, and an easy to install and use GUI to control the software interface, allowing the user to measure, validate, and control all of the functions of the powerful IC within minutes. Contact your local Enoki Wave sales office or distributor for more details, and happy integration.